So my name is Behan Webster. Amongst other things, I'm an embedded consultant and a trainer for the Linux Foundation. EALE is an idea that we came up with roughly 1 year ago. It happened because essentially a number of the trainers that we have for the foundation were standing around at another conference, and we thought, you know, it'd be really nice if we had classes that would allow us to talk about the kinds of things that we don't normally talk about at these conferences, and that is, you know, some of the things that are very straightforward for people who have been in the business for 20 years, but perhaps not so much for people who are newer to the area, or perhaps people who are moving laterally from another embedded part of the embedded ecosystem. And so we had all the best intentions in the world to actually get this all ready and done ahead of time. And what really happened is that in February, we thought, hey, maybe we should get started on this. And what happened a little bit later after that is somebody said, hey, wouldn't it be great if we had a cape for, you know, the pocket, we could use the pocket vehicle, we could build a cape. And so 6 weeks ago, we actually put together the beginnings of the hardware kit that we have here. We had the original Rev 0 of the board roughly, what, three weeks ago? We then got everything else into production, and in fact, these boards were built last Monday, put together. We picked them up on Wednesday on the way to the airport. Jason, the previous speaker, picked them up and brought them. And we used them first at scale last week and now this week. So please bear with us. There's a number of last-minute things that we're still trying to figure out and to make everything work. But hopefully we can show you all these things get put together. Quite a few of us work on the road quite a lot because we do a lot of corporate training. You will find that most of my slides, and indeed the thing I'm putting together, the Pocket Beagle this morning, in fact, a lot of these pictures are actually taken on my phone in my hotel room, wherever I happen to be. This is, in fact, the embedded kit that we use at the Linux Foundation on top of my laptop case under a lamp, okay? So that's what all this happens to be. We do a lot of these things with the gear that we just have with us. Today we're actually going to talk about kernel modules because this is one of those gateway things to actually doing kernel development. So what the heck is a kernel module? And really what a kernel module is it's a way of actually getting information into a kernel. And normally people think of code, but in fact data, you know, strings, library functions, drivers, there's all sorts of things that are nice to get into the kernel through a particular mechanism. Now, originally it was done for various reasons, including size reasons rather. We used to boot from floppy disks, and once the kernel got too big for one floppy, we had to go to two. One of the ways of doing that was loading some of the code onto the second floppy disk. We did this through modules. We also sometimes need the ability to, in fact, load things dynamically. Everybody sitting in here, I think, pretty much has a laptop sitting in front of them. And many people think of laptops as more or less being the same kind of machine. And broad strokes wise, they are. But in fact, they all are slightly different chips, different hard drive controllers, in some cases, vastly different hard drive and storage controllers, different kinds of memory. So sometimes there are things where we have to actually figure things out on boot up on how things work. And so you'll see, at least on all PCs and servers, we tend to have what's called an initial RAM disk, or a NIT-RD. In that are, in fact, drivers and modules that are used at boot up in order to take the generic kernel that was used in order just to get the initial RAM disk into place to actually take you the rest of the way and boot the rest of the system. Okay, and that's only really possible because we have modules that we can load from that RAM-based file system. We also have situations where we have more than one driver for the same piece of hardware. And in these particular cases, we need a way of being able to load one or the other based on a series of rules, and then have them work. Now, if they were both built into the kernel, of course, it'd be much harder to make those kinds of things work. So conflicting modules, again, nice to be able to choose. But the last thing that's the most important is that, in fact, by having modules, by designing your code in a modular way, we actually end up having a cleaner, better way of building a kernel. So the next thing, of course, is we often get asked about drivers and modules, and a lot of people think of they're the same things. Aren't modules just drivers, right? Or aren't all drivers modules, and so on? And the reality is that most drivers are actually written as modules, perhaps not the early ones, but the most recent ones are. And the reason that we write drivers as modules is primarily because writing them the original way was kind of annoying. Because what you'd do is you'd write code for your hardware, you would install your kernel, you would reboot. It would fail, you'd go back to your old kernel, you'd load things back up again, you'd write your next code and so on, but there'd be lots of these reboots over and over again. And that was kind of annoying. So the nice thing about modules is, in fact, you can write your module, you can load it, you can test it, you can unload it, fix your code, do it again. It's very fast. Now, before these were in wide use, in fact, one of the other mechanisms, especially for core code where you can't use modules, the other one, in fact, is using a hypervisor, right? Using a virtual machine. So again, rebooting a virtual machine much faster. However, for the vast majority of drivers, we still want to use modules because it makes things a whole lot simpler. But the big thing to understand is that a module is merely a payload of bytes, getting them from user space into kernel space. And that payload can be whatever you want it to be. Most drivers are modules. Some modules are drivers. All right, that's the way to think of it. You can do just about anything with a module to get some kind of thing, whether it be library code, a driver, a K-probe, right? Extra data. There's all sorts of things you can get in there through a module. So here's a very simple module, and fortunately our screen's a bit bigger than it was last week. Now again, if you can't quite see this from the back of the room, look at the slides that we have online already. And this is a very simple driver, module, and it illustrates quite a lot of things all at the same time. When it comes to reading modules, it's best to start at the top, and that's because this is where we find our include files. And there's two things we can tell from these include files. First of all, this is a module. We know this because it says include module.h at the top. This allows us to do one of two things. We can build it as a .ko file, a kernel module, or through Kbuild, we can build it as a built-in into the kernel, so it's always there. We know that merely because of that top line. The next line down that says init.h, we know that this essentially has initialization and exit code in it. Okay, and that's what is in the init code. And we're about to look at that machinery, and that's where it happens to live, is in that header file. I then like to go to the very bottom of the module, and down there you normally find, by convention, the metadata about the module itself. And there's a number of pieces of metadata, but probably the two most important is module author and module license. Module author is because primarily the person who wrote it, of course, is the person that you potentially want to send patches to, or bug fixes, or bug reports, or what have you. But more importantly, the module license is quite important because it dictates the license under which the code can be used. And this is very important because we have a number of symbols in the kernel through the in-kernel linker that will only tie to compatibly licensed pieces of code. Now, we think of the kernel as being all GPL v2, and the code that's in the actual main kernel is. However, when third-party code comes in through modules, of course, there are other licenses that are sometimes used. And there are ways that are used to actually restrict what you're allowed to do based on what module, what license your module has. Okay, so choosing a GPL-compatible logo is license rather is important. And there's actually 6 of those, and we'll look at those on a future slide. The next two things up here, these are actually macros. You'll see we have module init and module exit. Both of them dictate the name of the function pointers that we are going to use in a second. Our initialization code and our exit code, right here. Now the neat thing about this is in the past you had to have specially named init and exit code. These days you just use these macros, and in fact it will use function pointers to dictate what your initialization and exit code is. So in fact their names don't matter. And in fact you'll notice that we have made them static. And for those of you who know C, of course, you'll know that static, of course, is a scoping mechanism. It means that these functions are in fact available within this compilation unit, within this file. But in fact, they're not global past the edges of the file, right? So in fact, their names don't matter. They don't get added to the global symbol table from a cross-linking perspective and so on and so forth. So that's actually kind of interesting. So let's look next at return codes for both functions. And you'll see here that we have a return code for the initialization function of an int and void for exit. Now these are kind of interesting because of course you'd think that under any error circumstances you'd want to tell somebody how that, whether or not something happened and what it was that did. Now in the case of initialization, there are plenty of situations where there are errors. Perhaps you don't have enough memory, perhaps you're trying to talk to a piece of hardware and it's not there. Maybe it's a different version of what you're expecting. Maybe the parameters passed to you were incorrect. Any of those things, right? And so you have to have a way of pushing back and saying, actually, this isn't going to work for me. And so init has to have a return code that says everything was successful. Now, who here knows what success is in Unix? What's the return code that represents success? Right, and that makes sense because the return code represents, has there been an error? 0 means no, there hasn't. Okay? Now, positive numbers often mean that there's still success, but usually there's a length or a size or something like that. How many bytes did I read or write, and so on and so forth. However, negative numbers are almost universally used to indicate that there's been an error of some sort. And in fact, the error codes that are used across glibc and the kernel are the same. And in fact, those are the error codes you're expected to send back, right? So if you run out of memory, what do you return? enomem, minus enomem rather, which is minus no memory. And then everything through the kernel and indeed through glibc, which of course is what you're using when you're using user space tools, understands what it is. In fact, you can print it out in English, or indeed if you set your language to something other than English, it will print it out in whichever language you want. So using those standardized error codes is a very good idea. But the interesting thing is that if the initialization code returns anything other than 0, okay, the module is removed. Okay, essentially the module initialization has failed and it is removed. In user space, if you make a mistake, okay, and you've got open files and you've allocated memory and all these other kinds of things, you've taken out file locks, what happens when it dies? The stuff's cleaned up for you, right? The files are closed, the memory's given up, right? The locks are released, all those good things. In the kernel, that's not true, okay? In the kernel, because we are not in a protected mode system anymore, you have to undo everything that you do. So if you allocate memory, you have to deallocate it, all right? So if you allocate memory successfully and then you do something next where there's a failure, before you return, you have to undo everything that you did prior to that before you return the error message, okay? So you have to clean up your own mess. You can't get away from that, all right? Otherwise, you lose memory. Otherwise, you lose locks. Your resources start to disappear, okay? Your exit code is not called for you. You have to do this in your error code in your initialization. Okay, exit, notice you'll see there's a void. We're going to see in a little while that in fact there's a reference count on references to memory in the module. And in fact, once that reference count is down to 0, it is assumed you can remove the module, and therefore removing a module always succeeds. Okay, so you have to write your exit code in such a way that it is successful, or if there is an error on removal, that you can deal with it, because essentially your module is being removed whether you like it or not at this point. Okay, so make sure your reference count always reflects whether or not you can, in fact, be removed. Okay, so that's great, but the next really and you'll notice, of course, that there's no parameters passed in. Both initialization and exit have no parameters. The only things left over are these little underscore init and underscore exit, which are right there. And these are actually called attributes, and they are added into the symbol that it's actually freeing up memory there. That's exactly what's going on. It's actually freeing up the initialization memory at that point. Let's look at some licensing now. And there's actually 6 different licenses that are currently used, and the actual way they're called and dealt with, of course, can be argued with, but this is how it's referred to in the kernel. You have GPL, GPL v2, GPL and additional rights. These are all GPL v2. The first one, of course, would be dragged along to whatever the latest and greatest GPL is, if you don't specify it. The second one means GPL v2 only. All right, you'd actually have to get the person who owned the file copyright-wise in order to change the license going forward. And in the third case, it's GPL v2 and some other rights that you add on top of it. Okay, written, whatever those happen to be. The last 3 are referred to as dual GPL along with one of either BSD, MPL, or MIT. In the case of the kernel, we choose to use it under typically the GPL v2. Okay, but you'll see that all 6 of these, in fact, are GPL v2 compliant, which allows them to work along with the kernel. Everything else is termed proprietary, whether or not it is in fact a free software license or not. The fact that it is GPL incompatible means that in fact the code will not run with the GPL symbols that are inside the kernel. And we'll see a bit later that when we export symbols, we have the option of making those symbols GPL specific. In other words, if you do not have your license set appropriately, you cannot use those interfaces. Okay. Also, we have a mechanism called Taunt Bits, and Taunt Bits are on the right here. They indicate whether or not a license will taint the kernel. You'll notice the last one does taint the kernel. And this all goes back to the original time of the Linux kernel, when drivers from vendors were largely done as binary blobs from the various hardware manufacturers, because this was the normal way of doing it in Windows. Despite the kernel being GPL v2, essentially there was an exception granted by kernel developers because they wanted people to write drivers for the kernel at the time. And over time, it's actually seemed to be perhaps a bad idea. And the reason, unfortunately, is because when something crashes, you don't know where it's crashed. Is it in the code that we can get to, or is it in the code that we can't? Right? Unless you have all the code of what you're dealing with, it's very difficult to know what's going on. So you'll find that a lot of upstream kernel developers, especially kernel developers that don't have access to your specific code, if you send them an oops, right? If you send them a bug report, the Taunt Bits are associated with that oops. And essentially, if there is a Taunt Bit set for license, that means that there's proprietary code in there. It means that they can't get to the source code. That means they can't really help you, and they're wasting their time essentially trying to. All right? If Taunt Bits are set, usually a kernel developer will tell you, try to reproduce the problem without the Taunt Bits, then send me the bug report again. Okay? However, if you can't reproduce it without the proprietary bits added, go look and talk to your proprietary vendor, because the code problem is probably in their driver. It's a way of making sure things work. So Taunt Bits, the first one that was added was actually for proprietary modules. That was the whole reason it was added. And that's purely because allowing proprietary code into the kernel was problematic. Okay, is it a good thing, bad thing? Is it legal or illegal? We'll just sidestep that whole thing for the moment. It's a pain. It causes problems. It makes my job harder. All right. So regardless of where you stand on that particular spectrum, it doesn't matter. It's still annoying. Okay. Now, once we had this mechanism, a lot of other things were added. A lot of other Taunt Bits, because there's a lot of reasons why some things can have problems. And I always like quickly telling the story here of, well, it's a story about a polar bear. Anybody know about Binky? It's funny, almost nobody knows this. So in the mid-90s, there was a polar bear in an Alaskan zoo. His name was Binky. Look it up. It's on YouTube. It's in Wikipedia. I'm not making this stuff up. Okay? Polar bear. And the really neat thing is that he was in a cage. And so Binky had this cage and these big bars. Okay? Quite big. You could almost get between them. Big bars, and then you go back a couple of steps and there's a fence. On the fence, it has a sign. And the sign says, polar bear, danger, do not cross fence. And then a few more steps, another fence. Okay? This is where the humans are. Polar bear's over there. Okay? The reason why Binky became famous is because there was a situation where somebody had crossed not just the first fence, not just the second fence. They actually had put their arm through the bars and were taking a picture of the cuddly, fuzzy polar bear that was taking a nap. And they looked back, looked back, and the polar bear was trying to pull them through and have a meal, right? Try to eat them. And they eventually got the polar bear, Binky, to let go of the woman, and she survived and went to hospital. Unfortunately, there was a certain element of people in the southern states, in other words, not Alaska, that were calling for Binky to be destroyed because Binky had, of course, attacked and almost killed a human. That's fairly common in our societies. The Alaskans, of course, were the opposite. They sort of said, polar bear, they eat humans. That's kind of the reason we carry rifles with us when we go out in the middle of nowhere, right? There were 3 fences. She didn't read the signs and stuck her. I mean, it wasn't Binky's fault. That's normal, right? That's just what polar bears do. And essentially, that's the way it left. And there's further parts to the story. The whole point is that if you're warned, right, and you still cross the fence and you get eaten by a polar bear, it's your fault. It's not the fault of the polar bear. And that's what the taint bits are all about. Let's look at some of these other ones. Taint forced module. There's a mechanism where you can use older modules in newer kernels. And there's a whole mechanism that tries to see whether or not that's safe or not. Now, if the kernel says that it's not safe and you decide to ignore that and force the module into the kernel, maybe you know that it's safe. The point is you still did something that's not good. You still crossed that first fence towards Binky the polar bear. Okay? The next one, taint CPU out of spec. Again, you're not running the CPU. Maybe you're overclocking the CPU or something. Again, you're doing something that's inadvisable. Again, you're taking a step towards danger. Okay? So again, it's recorded. And it's recorded in the module, and it's recorded in the kernel itself. So if you add the module and then remove the module, the taint bit's still there. Okay? You then have things like force RM module. So remember I said you had to have the reference count down to 0 before you could remove a module? Okay, if you look at the man page, there's a force remove. Again, if you really know what you're doing and you really feel very strongly that you should be able to remove the module and not cause problems, it's your right to do that. Unfortunately, it still sets a taint bit, and the reason is because you're probably wrong. Okay? In my career, I've force removed a module, I think twice, and I've been correct. All right? Every other time my kernel has actually crashed. A machine check, right? An MCE, it means there's bad hardware. Bad page, right? Bad memory, right? If we know there's a hardware problem, if there's a problem going forward, it's very possibly hardware related. Taint user, okay? So you can actually set a taint bits from user space. Taint die, things died in the kernel. Taint overridden ACPI table, again, you're ignoring what the ACPI tables say about your hardware. Taint warn, so something that was perhaps a problem, but we don't know, right? And finally, taint crap, and this was for everything else. They didn't want to add any other taint bits, and so everything else was crap. Okay, and if you look for bad words in the kernel, this is probably one of the least bad words. Okay, but anyway, that was for the longest time, that was the last taint bit. But for the last couple of years, every time we go back and look at the taint bits, new ones are added, and we start getting them over and over again. And about 2 years ago, they added taint firmware workaround. This is to work around boot firmware on PCs primarily. Later on, we had OOT. Anybody know what OOT stands for? Out of tree. Okay, so building a module out of tree, not in the kernel, taints your kernel. Guess what we're doing today? We're going to be tainting our kernels. Okay? Unsigned module. We have a way of signing kernel code right now. Okay, the problem, unfortunately, is let's say you're running in a Fedora or Ubuntu kernel. Do you have the signing key for that kernel? The answer is no, you don't, right? Only they do, because of course, only they have the ability to indicate what is a valid piece of code from them. If you had access to the kernel key, so would every other hacker in the world, and the point of signing your kernel is kind of pointless then. So if you made your kernel, you have your own key. Somebody else has, you probably don't, okay? If your kernel is set up to allow unsigned kernel code into the kernel, of course, it will set the taint bit that, in fact, you've allowed uncontrolled code into your kernel. Soft lockups, these are primarily done with multi-processors, CPUs. Again, if one of the CPUs locks up, we can often recover from that, but again, there's been a potential problem there. Live patching, this is another kind of interesting thing, something that I'm not very happy with. I used to work in telecom on live patching for telephone switches about 25 years ago. And great idea if you're going to get fined if you otherwise reboot, which is why we did it in telecom. In modern Linux servers, However, we have this problem, and the problem is if you turn the server off at the wrong time, bad things can happen, right? Maybe 911 service goes down. Maybe we lose access to top-level DNS servers. Maybe Twitter goes down. That's the worst, right? So you have to wait until your maintenance window before these things happen, right? And so as a result, how do you mitigate the kinds of problems that we have through CVEs? You just can't have Google reboot all of its servers in the next 5 minutes because of some huge problem. So instead what happens is people can come up with live patches. And these aren't modules. These are the way of actually patching the running code path so things happen. But of course what you're doing is you're causing all sorts of potential problems going forward. You're actually sticking a jump in the middle of an actual active code path to make things happen. Okay? And again, you're starting to do uncontrolled things to your kernel. Again, potentially bad things could happen. It's meant as a mitigation mechanism, though, until your next maintenance window. Again, we set a taint bit to make sure it happens. And then taint auxiliary for lots of other kinds of situations. There's actually, I think, one other taint bit I left off as well. But every time a new taint bit's added, you have to go and look and see what it means. Okay, and they're just bits in a 32-bit word. Is really all they are. And so you just have to know what they all mean necessarily. But when you look at oops messages, you will actually see them set in them. But that's an important thing to have. The next thing is I mentioned the in-kernel linker before, and there's actually multiple linkers we use when we build modules. The first one is in bin utils. So when we build something, let's say with GCC, it's turned from a .o into a .ko, and we do this by linking not only your code, but also a bit of generated code together into the .ko, the kernel object, the kernel module. Okay, so that's the actual linker that you're all used to using. However, there's also a linker in the kernel itself that's used for putting the modules into the kernel itself, and it uses in-module symbol tables to make the fix-ups occur and work. The big thing to understand is that as far as the kernel linker is concerned, all of your symbols are essentially static. They're not global. This is one of the reasons we make them explicitly static in our code, because they're static anyways. All right? The next thing, of course, is understanding that as a result, in order to export a symbol to the greater kernel for them to work with the linker, we then have to explicitly export them by using the export symbol macro that's right there. And that will work on both data and on functions. It doesn't matter either way. However, let's say you want to actually use that GPL symbol thing I was mentioning about earlier. If you actually export symbol GPL, it means now that only GPL licensed code can link to you. So if you are using a license other than those 6 we looked at, and you actually try to link to that code, in fact, you'll get an error. Essentially, your initialization code will fail. Okay, in fact, it never gets run. All right, so this is why it's important to think about your licenses and how they work, because essentially, the world of your code is actually getting smaller and smaller. And the thing that I always find interesting is that the people that tend to use export symbol GPL, a lot of them are people that are in the free software world. But I always argue that it would make a whole lot more sense for companies to use it. Think of it this way. Let's say you're writing code that you're concerned that your competitor might use to make a faster, better, whatever, based on the code that you've contributed to the kernel. If you say that it can only be used under the terms of the GPL license, that means that they have to play this by the same rules that you're playing by. Why would you allow them to link their proprietary code to the work that you've done if that could potentially hurt you? Wouldn't it be better if you could essentially force them to actually use the same rules that you're releasing your code under? Makes sense to me. Okay? So it's actually quite an interesting thing. However, it's also considered bad form to change from being non-GPL symbol to a GPL symbol. So we actually have a symbol GPL future. And the general rule is you're supposed to mark something as GPL future for 2 versions of the kernel before you actually make it a GPL symbol. And this means that if you are actually following the kernel and not just jumping, vast versions, that in fact, as you go forward, you'll get a warning as you link your proprietary code to this. They'll merely say you're trying to use a GPL future symbol, which of course means it's going to be a GPL symbol eventually. Okay? Always good when you're doing work on the kernel to have one person on your team and have him or her actually try to keep up with the latest and greatest kernels, because you'll see problems like this before they actually become an issue. Okay? There's a bunch of other export symbol macros. They're edited out just to make things faster, but there's probably another half dozen of them or so that allow you to do different things. The next thing we're going to cover quickly is Kbuild, and we mentioned that briefly, but it's the overall build system that's used in the kernel. It's very useful because it makes the make files in the individual directories or subdirectories very, very simple. It means that most of the build machinery is kept under the scripts directory, under the maintainership of the Kbuild maintainers, and it means that all you really have to do is list which files you want added as built-ins or modules, or what flags you want to add, and so on. So most of it's very easy to read. I'm sure everyone here has probably worked on a project where makefiles sort of got out of hand. If you look at the kernel code, you'll find that the makefiles are actually very straightforward, and it's because all the out-of-hand stuff is hidden elsewhere. Okay? So the really cool thing about this, though, however, is it means you can centralize your build configuration, and this is done in something called .config, and it's specified by a mechanism called kconfig. Kconfig allows you to have a series of files that describe what each configuration option means, what it does, where it is, any kinds of dependencies and other things it has on it. In order to choose those configuration options, we have a number of different, effectively graphical mechanisms for doing it. I'm sure many of you, who here has actually compiled a kernel before? Okay, so menu config. Who's used menu config before? Okay, so there's a few others as well, obviously. Many of you will know that there's also xconfig, nconfig, sconfig. There's a ton of them. The reality is that menu config is the one you'll find in most how-tos. It's also the one that is supported in other projects more than any of the others. All right, so if you want to use one of the other front ends, great. Just understand that by knowing menu config, it is more portable across other projects. All right. The really cool thing is almost all embedded projects, in fact, now use Kbuild and therefore menu config in order to configure themselves. The most notable exceptions to those, of course, are things like Open Embedded and Yocto project, which we will cover on Wednesday, actually, sorry. Buildroot, on the other hand, uses menu config, as does BusyBox, UCLibc, CrossTool, and a bunch of other things. Uboot uses it, right? Everybody uses it. All right, so here's your .config file. Here we have a configuration option, and by default, all options in a Kbuild environment start with the same prefix. In the case of the kernel, it's config underscore. In this case, we've got a variable or a configuration variable called foo. In this particular case, by setting it to M, we are indicating we want it to be a module. In other words, a .ko file. Later on in the make file, we would have something that looks like this. You'll see we have an obj dash. In this case, we have config foo. So of course, it's set to M. So when we actually run the make file, it will be added. This plus equals foo.o will be added not to obj dash, but to obj dash m. Obj dash m is in fact a list of .o files you want made into kernel objects or module files. You can also just straight up, of course, add things. In this case, we're saying bar is going to be a built-in always. And you'll see down here, we can also add directories or subdirectories. You add a postfix of a slash. This indicates it's a directory. And essentially, if config blah was set to, wasn't set to yes or module, in fact, the subdirectory or submenu that was under that directory would never be shown. So we have ways of excluding files and, in fact, whole subdirectories of things merely through looking at how your make file is put together. There's a whole bunch of documentation on this in the kernel Big D documentation directory that talks about how to do it. So Big D documentation, Kbuild, a bunch of stuff on kconfig. Okay, Kbuild. Kconfig, of course, is a part of that. It allows you to specify a number of things, including things like the type, the short version of what the configuration option is, any defaults, help, dependencies. You can do different kinds of conditionals and such on things as well. Here's an example of one, config foo. It's a very important option, foo. You'll see it's a tri-state. This means that it can be either a built-in if it's set to yes, a module if it's set to M, or it can be configured out by unsetting it. You can notice there's no N, strictly speaking. Okay. However, you choose the three states in menu config by pressing Y, M, or N, and turns it off. You can also toggle using the space bar. You'll see that we can set, we also have the one-line description up here, you'll see. This is actually used in the configurators like menu config. We have the default here, which is set to module. You'll see here it depends on blah. This means that blah has to be set before it will actually even show up in the menu configuration. All right, so if blah is unset, this option isn't even available. All right, we also have a select, in this case floop. I ran out of names. So select means that if we turn on foo, it will in fact also do the same thing to floop. Okay, so in other words, if they were both no and foo was set to yes, floop would be set to yes as well. All right, now if floop was already set to, let's say, module, then it's already selected, we're all good. Okay. So we don't have the mic up here, but the question is, we'll change it to a built-in if the other one's made into built-in. No, if it's already a module, it already has a value, and therefore, actually, sorry, pardon me. If foo is set to yes, yes, it would have to become a built-in, because otherwise the dependency wouldn't be satisfied. I'm sorry, you're right. You're correct. Just have to think about these things logically, and it makes sense. Next, select bar if not baz. So in this case, you're saying we're only going to select bar, however, only if baz is not set. There's very complex sets of logic you can put into place, and the idea is that kconfig can ideally be set up in a situation such that you can't choose conflicting configurations. However, that's obviously a very large matrix to get right. We also have help. You'll find down here it says help, and then we indent our help. The reason is because the next line where config is at the beginning of the line is where the next configuration option begins. And as a result, help is in a bit, and it can be multi-line, and it means we have a way of adding multiple paragraphs of how things fit together. And again, just as long as it's not up against the edge of the screen. This is menu config here. You'll see here that we have a number of different line items here. The up and down arrows will take this blue bar up and down this way. The left-right arrows will take you across the bottom. You'll see that by default it's on select. This means if you go down to something where you can make a change, like this square bracket part here, it's currently turned on to yes. Square brackets mean a Boolean, so pressing the space bar or pressing Y and N will allow you to toggle this on and off. The one that it's on currently, you'll notice, is a dash star dash. This means that it is a selected option turned on. In other words, you cannot turn it off. It's on by somebody else depending on it, or having selected it. If these were angle brackets, in other words, less than or greater than, it would be a tri-state. In other words, it would go from off to module to yes, back to off again, if you press the space bar. And indeed, you'll notice we have little arrows off to the right here. This means these are submenus. If you press enter when you get to, let's say, if you go down and press enter on general setup, it will take you into that submenu. Now, it's a few other things here. And the first thing, of course, is there are an awful lot of configuration options. There's well over 10,000 of them. Any particular kernel has at least 3,000 of them. And I say at least because they can get a lot bigger. Now, in the past, it was quite straightforward. Everyone would remember where everything was, and it was, you know, you sort of knew how much somebody knew a kernel by remembering which submenu everything was in. These days, things are moved, things change, things disappear, new things are added, they're renamed. So finding things is rather difficult. So having some kind of search mechanism would be really fabulous. And so essentially, eventually they added a search mechanism. Who knows how to search in menu config? Right, okay, so essentially it's the Vim way, right? You type in your option, away you go. Turns out the case doesn't matter, you don't have to put the config part in. As long as you type in something that's vaguely like what you're looking for, it tends to find at least one instance of it. Now, if it finds more than one instance of the variable that you're looking for, it will actually list them, and you can use the arrows to go up and down the list. And what it comes down to essentially is each thing it finds, it will tell you what the variable is, what the current state of it is. Any things it selects depends on what it's currently set to, where it is in the file. It'll tell you which subdirectories it's under, which submenus it's under, and so on. However, in the past, you always had to then go escape, and then you had to actually go and find it in the menus. And that was always a pain because, of course, those of you who've done this before know that there's nothing sorted, right? It's in no particular order. Again, you just have to know. So the really fun thing is that they added a mechanism that allows you to actually jump to an entry a lot faster. And I still remember being at, and I believe it was the Embedded Linux conference, we were in a talk where the front few rows were all kernel developers. And there was another kernel developer on the stage, and they were showing their latest and greatest thinking, going through this demo, and they went into menu config to turn on their thing. And he did a slash and searched for his configuration option. And then all of a sudden it jumped to his configuration option. And he kept on doing his talk, and one of the kernel developers put their hands up, and I don't remember who it was, but it was one of the more important kernel maintainers. And he said, "Wait, go back. what did you just do? Okay, and it turns out, and pretty much everybody has now done this, is if you look at that search thing, and right next to each option of where things are, you'll see a little number. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, and so on. You press the number or letter that's there, and it jumps straight to the thing you want. And this is how most people do these things these days. Because does anybody remember where these things are anymore? Very few, right? And so this is a very good way of jumping around inside this. And now that you know these tricks, you'll always know how to find what you're looking for. Okay, and again, just search for the thing that you think it probably will be called, and you'll probably find something in there. So again, we have a slide here for people looking at the slide deck later, basically what I just said. Now, as far as building a module in tree, typically this is how it works. First, you add your code into the tree itself. You add your metadata into the kconfig file. The kconfig file is literally called kconfig right next to the make file. You then, of course, go into whatever your configuration thing is, like menu config, wander around until you find your option, set it to the value you want, and of course, that will then, when you leave the tool, will write that variable into the .config file. And then you build your kernel the normal way, and it will either build it as a module or a built-in, depending on how you've configured it. Are there any questions so far? Okay, so can we get the mic up here, please? Certainly, and again, please ask questions as they come up.
Okay, so is it taboo to, I take it it's taboo to directly change the .config file. So I mean, if I find something that's like, darn it, I don't want to go through make menu config, I'm building my kernel, I just want to hack
Sure.
N to Y.
I understand. I've seen a lot of people do this, and normally it's because people don't necessarily know how to use the configuration options that are there. Usually people don't know how to use /search is quite often the reason. It is in fact possible to change the configuration file directly. Just understand that because of all the dependencies, the conflicts, the conditionals, and everything else, as a result of changing the file directly, it means you have to go through a step where it will, in fact, have to go through and figure out whether or not your configuration file is even valid anymore. And so what happens is that, and then ask you questions. And so the point is if it's a very simple thing you're changing, in fact, it doesn't know the difference. However, if you're changing some fundamental thing, like let's choose a ridiculous thing. Let's say you change the architecture in your .config file. That has an awful lot of cascading effects, right? That effectively means that your .config file is completely wrong now, and it has to go through all sorts of machinations to make things work. It tends to go through a set of asking you new questions because all of a sudden new things have popped up. But what I'm trying to say is can you do it? Yes, you can. Should you do it? It's a bad idea. Okay?
Make menu config is a dependency checker as well.
It does. And in fact, when you take an older kernel configuration file and actually build a newer kernel, one of the first things it'll do is what's called an old config, and it'll go through and ask you questions about new things. It will remove old things and so on. Honestly, what I do, and I've seen a lot of other kernel people do the same, is they just run something like make menu config, which will take all the defaults, and literally I jump into menu config and then straight away save. And that does exactly the same thing but faster, and it's better than just holding the enter key down when you're going through old config. Because quite often what you want is those options anyways. The defaults are usually pretty what you want. And if they're not, you know what you're looking for and you go and change it anyways.
For debug symbols, do we need to do anything special in symbol definition or in?
For what, sorry?
Debug.
For debug? So if you're debugging a kernel, we're actually going to do a thing on debugging tomorrow morning. You can debug a kernel without turning on debug info, but it's usually not very much fun. Debugging info actually adds debugging symbols to the kernel itself and actually makes these things available. Typically, it's in the uncompressed kernel object that you use with the debugger, so it doesn't actually go into memory necessarily. But you don't have to build with debugging symbols. It will just make your build take a lot longer and make everything take a lot more space. So unless you're actively debugging things, most people don't build debug symbols in. You can still use debuggers. It just makes it harder. Yeah. Oh, okay. Behind you? Yeah.
Are there certain taint bits that are more lowly regarded than others?
No, not really. Basically, if taint bits are set, that's a problem. Now, it doesn't matter if it's an out-of-tree module or whether it's a proprietary module. The reality is that a kernel dev can't easily help you. Now, if it's something, let's say it's innocuous, like let's say it is an out-of-tree module taint bit, but they've also included the module they used in order to, along with the kernel. As long as people have access to all the source code, it's fine. Okay, but you'll find in that situation what a kernel developer would probably do is say, well, put your code into the Git repository, give me access to the Git repository, and then we'll try it, sort of idea. So generally speaking, any taint bits are bad. If you can explain them and such to yourself, then that's great. But a third party isn't going to want any taint bits set.
Okay,
that's pretty much the deal. All right, let's build a module out of tree now. And the way we do this is essentially, the way we do this is by understanding how the build system works. Now, the neat thing about the build system in the kernel is that it is actually made a part of the actual kernel headers themselves. We're used to kernel headers just being .h files, but we have this problem in the past where when modules were first conceived of course, you can build a module, but you need to know exactly what the configuration options are, what compiler is used, what options to the compilers are passed in, and all these things, all these stars have to align to make it work appropriately. All right? And so you just had to know the incantation to make it work. And that didn't work very well, obviously. It's not sustainable. And so the other way of doing things is actually to build into the build system those kinds of options such that when you were building your code over here, it's in fact using the live running kernel configuration that's over here. And so if you actually look at your kernel headers, once you've built your kernel or you do what's called a module prepare, it will actually build what are called configured headers. Configured headers are essentially just the kernel without actually building any of the .o files, where you actually have things like your version.h file has been created, your autoconf.h file has been created, and so on. Okay. It also makes sure that your .configure file is there, and so on and so forth. Your .config file, rather. And so by having access to all that information, including all the scripts used to build the kernel in the first place, we now have a way of replicating the ability to build a module, but not in that kernel tree. So our kernel headers are over here, and they're configured. All right. They're configured in the same way as the thing that we're building for. We've got our module code over here. All right. How do we make this work? Well, you'll notice here we're doing a make modules, but there's some stuff in between. The first thing is make -C kroot. Now up here I've actually specified the path to my headers. -C means change dir. So instead of, if I'm in my modules directory, I'm not running the make file here rather. I'm running my make file over here in my kernel directories. Okay. So, however, I want to build my module code that's over here. So how do I do that? Well, I specify this variable called m. And m is short for, because good developers are always lazy, kbuild module. Okay, kbuild underscore module takes way too much typing. So m equals a string, of course, is far better. You'll notice that we're using pwd to get the directory name of this thing stored in the m directory, walk over to the kernel directory, and then therefore run make modules to build the code that's back where we just came from. Make sense? Okay, so there's a lot of moving parts there, but that's essentially how that works. Cross-compiling modules, there's a few extra variables that you need. The first one is the arch variable. The second is the cross-compile module. And until you'll see that it's the same sort of thing, -C, that should be a kroot. I'm sorry, I just noticed the error there. M equals pwd again, same as before. But however, this time you'll see there's an arch equals arm. Architecture, of course, indicates what we're building it for, what kind of CPU. If you look under the arch directory in the kernel source, you'll see a number of subdirectories. Normally, if you're building on an x86, you're using the arch x86 architecture. Let's say you're building for 32-bit ARM. Setting arch equals ARM means it's going to use that subdirectory instead of the x86 one. All right, and in fact, part of Kbuild, in fact, lives under that, specific to ARM or x86 or what have you. The last thing you'll see here is this cross-compile variable, and you'll see that we actually have what's called a triplet that's passed into it. And through this triplet, we know that we want to compile for ARM, We want to compile for a kernel, right, as opposed to being a bare compiler, working on a bare ARM. We also know that what our user space libraries are set to. GNU indicates that it's glibc based. EABI, in fact, indicates that we're using the newer of the two ABIs that ARM has. Before we had EABI, the old ABI didn't have a name. Now it's called OABI, old ABI. We're very good at naming sometimes. EABI stands for Extensible ABI, so anyways, or Enhanced EABI. ABI standing for Application Binary Interface. Okay, so there was a new calling mechanism within ARM that was more efficient and therefore faster. And you'll see the two things at the last, the HF stands for hard float. In the past, and in fact, even now, ARM does not require you to have a floating point unit. However, these days, for V7 processors and up, everybody has an FPU. Everybody has a floating point unit, therefore, doing software emulated floating point really isn't very useful anymore. So in this case, we know we are building Linux binaries for ARM with glibc using the new calling convention with hardware float support. Okay, and the dash at the end is important because, in fact, that will preface all of the tools we're using. In the case of GCC, we will end up running the tool ARM Linux GNU ABI HF GCC. Okay, so that's how that all works and how we actually can specify which part of the build system and code we're using, and in fact, which compiler we want used instead. Now, as far as installing a module is concerned, let's go through a couple of the tools before we get onto the labs. And the first thing is, what does the word install mean? Because I often find people get two terms mixed up. There's the idea of installing a module and inserting a module. Okay? Now, installing is very specific under Unix. Does anybody know what the command install does? It's a glorified copy. That's all it is. When you do an install during building something and then do the make install, you'll find that if you do a man on the install command, it's merely a copy where you specify user, group, and mode. So it's an enhanced copy program. It also allows you to create directories, again, in the same fashion. It's a way of doing it as an atomic step, effectively. All right? So when you install something, indeed when you install a module, you are merely copying it from where you built it to the place where the kernel knows where it is, the kernel user space utilities, in this case mod probe, and they will end up under, and again, apparently I forgot to fix the slide, this should be lib/module/ and then the revision of the kernel. So if you look on your machines, you'll find there's a /lib/module/ and then 4.15 or whatever kernel you're running that's under there. And in fact, that's what we're going to see on our little Pocket Beagles. You'll see it's actually a 4.9 TI kernel. All right, and so when you do this, you'll see that we do a make modules install. In fact, there should be a sudo in front of this because we always do this portion as root. We build as a regular user, we install as root. You'll see that we do a -C, the kernel root. Again, this should be kroot. M equals pwd, arch equals arm, modules install. Notice we don't need to specify the CrossCompiler in this case. Why? Because we're not compiling anything, we're merely copying files. All right, and don't get into the habit of doing a make modules install and expecting the compile to happen at the same time. You're building as root, okay? Remember, whenever you build something as root where you don't have to and you make a mistake in your make files, and I actually did this while I was preparing this slide deck. I was testing some of my work on one of these boards. In fact, I was talking to Robert at the time over the internet, and I went away for a few hours, and the reason is because I built a root file system for ARM, and then my install script decided to unpack it not in /media/ whatever, but under /. Yeah, that was a fun day. Fortunately, I knew how to recover from it, but it took me a few hours. Anyway, my whole build machine all of a sudden became a dual ARM x86 root file system. Not a lot of fun. So do not build as root, okay? And other thing is whenever you're writing install scripts, don't rush, check your paths, all right? If you're unpacking and your variable is set to /, it's probably wrong. Or empty string too. Okay, so anyway, that's the deal, all right? So build as a regular user, install as root. Just check your install scripts. Insmod, this is the one a lot of people think means install. It doesn't, it's insert, Okay, and install is a lateral copy from this place in the file system to over here. And insert is taking a module and putting it into kernel memory. Okay, I always think of the kernel being up. Why? Because the kernel lives in high memory. Well, low memory that's been shifted up. Anyway, the top part of address space. Okay, so what happens is insmod basically turns around, does a system call, and invokes the in-kernel memory. So it copies it into kernel memory, and the linker takes over from there. Adds things to the kernel symbol table and all that other good stuff. And so typically the way that works is, again, you have to run it as root, insmod, and then your path to wherever your module is. It could be in the local directory, that's fine. And then any options, any optional options you want to pass is done there. You can only insert one module at a time, okay? Because everything after that is modules. Now, before we get to the question over here, the modules have a name and a file name. And by default, we have a question over here in the corner here. By default, module names essentially are the file name .ko. The name of the module is typically the file name without the .ko. So when you're inserting things, of course, the thing has .ko at the end. When you remove it, you're going to remove just module name, not module name .ko. Now, it turns out, lazy programmers, in fact, you can leave the .ko at the end. It's just that it's not strictly correct. It just strips it off. Okay, the tools will strip off the .ko. However, there's a side effect of this. Do you know how it does that? If it finds a dot, it deletes everything from the dot onwards. So what can you not have in a module name? A dot, okay? I've seen that happen more than once too. So just keep it to alphanumeric letters, no extra punctuation and so on. A question, please.
When you run insmod, that's when it executes the underscore init.
The initialization, yes, so it links it in and it automatically runs the initialization code at that point, yes.
And then if you do an rm mod, it runs the
exit code.
Runs the exit.
Yes, yes. And what that means is if you take an oops during your initialization code, the oops will actually specify that the user space program that was running at the time of the oops was insmod, even though, of course, the code died in your code, not in insmod itself, because you're on the kernel side of things. Does that work? I have 2 more questions in the back. Oh, okay.
So if you're inserting into a running kernel, is it possible that there won't be enough kernel memory to set the module up?
That is absolutely possible. However, there's a real issue with that, and that is, in fact, if you're in a situation where the kernel runs out of memory as a module is being added and there's no way of freeing memory up, normally there's something called the killer that tries to clean up memory as you go. However, let's say for whatever reason that doesn't happen, you'll actually crash the kernel. If you run out of memory in kernel and there's no way of coming back from that, let's say you've exhausted all other options for reclaiming memory from the memory allocator or whatever, worst case, you could in fact crash your kernel. Yeah. Absolutely not. You just crashed. You're dead. Okay, we need the yeah, sorry.
Sorry, I mean, like if you have something like kdump set up already, will it show cleanly?
If you had a kdump set up properly and you were able to actually, and for various reasons, the kdump actually succeeded and didn't fail, you would be able to see that in your kdump. But normally the situation is dire enough at that point that you try to figure out what's going on. It's usually pretty obvious that it ran out of memory. Yeah.
Beginner question. So the kernel, inserting a module into the kernel because the kernel's made of modules, or what? Is the kernel made of modules? So there's always a core piece of the kernel that is built-ins. You'll find that on PCs, certainly there's an awful lot of code that comes in through modules. It's not completely made of modules. Things like the scheduler, the memory subsystems, and so on, these all are all build time choices and therefore always built-ins. So there are certain things that must be built-ins and there are certain things that have to be built-ins just so you can boot. So in other words... Are you using built-in as another word for module?
So in the case of a built-in, it's not a .ko file, it's actually a part of the LLVMLinux file itself. It's a term that indicates it's been linked into the kernel as opposed to being a separate file.
So the module is built in, or it's a
No,
different thing?
the module is a separate .ko
Okay.
file, and
And
so
the
we load that with
built-ins
insmod.
are-
A built-in's actually a part of the binary blob that makes up the kernel.
That you're specifying that when you make the config and all
Yes.
of
So by specifying a yes for a .o file, in fact, it will be compiled into the kernel such that it is there at boot time as a part of the kernel that's loaded from the bootloader.
that. Just one more question. Do you have an example of like a module, what it would do that you would put into the kernel?
Do I have an example of a module, or
Yeah, like what I mean.
so any file system? So for instance, NFS drivers. So your wireless driver, your let's say when you plug in a USB device. In fact, when we plug in our Pocket Beagle, you either get on Linux you'll actually get a CDC driver, which is the gadget driver for USB. You'll also get the RN disk driver for the Windows networking style stack that comes up. And so on. There's millions of them. Well, thousands of them. Yeah. Yeah, there's a lot of them that happen. So again, the more modular, the more you put into modules, the more flexible everything is. And the better your overall architecture is. But it's a very good question. Yeah.
So why not make everything as a module, or just make everything built in?
So why not make everything a module? Why not make everything as a built-in? So the reason why you can't make absolutely everything as a module is because you need something to actually support putting modules in the first place. So there's always a core piece of the kernel that always has to be there just so everything else works, right? And so for instance, let's say you have the core pieces of ftrace, the scheduler, the interrupt subsystem. These aren't things that we can make modules. They have to be there for everybody else to use. However, why not make everything a built-in? Because literally we cannot, if we built everything into a single kernel, barring the fact that there are certain modules that cannot be loaded at the same time, the kernel would be as probably rival the size of system memory that you have. You want the kernel as small as possible. Again, remember, memory is non-pageable in the kernel. So any driver that you add as a built-in, it's taking up space whether you use it or not. On an embedded system, we tend to use built-ins because we know what hardware is there. On something like a PC, we have no idea. We know that there's some kind of driver for graphics, but we don't know which one, not until we actually boot. Right? For instance. Another question.
So building on that last question, when is it appropriate to use a module? When is it appropriate to go embedded? Is there a general rule of thumb?
So is there a prevailing wisdom about whether or not a module should be used or not? Really, it's up to you. If you on an embedded system, the thing to understand is as soon as you upgrade the kernel, you actually also have to upgrade all the modules for that kernel on the root file system. If you know what the hardware is and it never changes, and you don't have USB, for instance, if you use a built-in, it means you never have to worry about modules now in the file system as well. One of the reasons why the Pocket Beagle is nice to upgrade via Debian, of course, is as you get a new kernel, the package system also installs all the new modules on the file system as well, and that's super. However, on a lot of traditional embedded systems, it's separate from the file system, and now you have to make a change to two things, the kernel and the file system. See what I'm saying? So really, unfortunately, your question was, is there prevailing wisdom? Is there a rule that you can follow in order to make it happen? The answer is no. It just kind of depends on the situation.
So if you're using a package manager like dpackage or whatever your OS has, then it could automate that for you.
Yes.
But otherwise, you have a separate step of having to
potentially
those additional modules. And
yes.
And if you do any minor revision of the kernel, the old modules are broken, correct?
The old modules will probably, well, they may be able to be used still through the module version system, but in general, yes. In general, you shouldn't use older modules of the newer kernel. In general, you have to replace those modules along with the kernel.
And that would, if you did manage to use them, that would set one of those taint bits?
If you force loaded them, yes. Yeah, it wouldn't do it otherwise. Now, we're going to probably get a lot more questions, and I do want to get onto labs. So let me get through a few more of the slides. When we get to the end, we'll try to set people up, and then we will answer questions just to make sure that we actually have time to do some of the labs. One of the reasons we're doing this particular course now is because we're going to be doing a number of modules tomorrow, and so I'd like everybody to have a chance to practice that. But I understand there's lots of questions here. So this is insmod. LSmod is the next thing, and this is quite useful because this tells you what's currently loaded on your system. Now, if you type LSmod by itself, you'll see probably the most recent thing is at the top of your list. This is because of the way things are put into the list. The thing at the very bottom was the very first thing added, and that's because it's actually a linked list in the kernel. In the kernel, our linked list structures actually pop things onto the front of that list. And so the most recent thing will be at the very, very top. You'll notice we have the name of the module on the left. We then have the size in bytes. And then we have one column that has two sets of things in it. The first thing is the reference count. And the next thing is, in fact, the other modules that are dependent, that are being used by that this module depends upon, pardon me. So UIO in this particular, UIO P drive GenRQ is currently using UIO or symbols from UIO. I call this a, what's it called? Well, it's a dependency, but it's an implicit dependency. The reason why it's implicit is because by UIO using a symbol, by UIO's P drive GenIRQ using a symbol from UIO, there's a dependency that is generated by the build system. In other words, when we figure out dependencies, we automatically know that when we load this, we need this module, and therefore there's a implicit dependency there. We haven't said we depend on this thing, but we do, and the build system can figure that out. However, you'll see we have a bunch of things that have just numbers, straight up numbers, but not a module name. And the reason is because we also have explicit dependencies. An explicit dependency is when you use an API in a particular module and usually get a reference to a piece of memory within that module. Those APIs tend to have reference counting in them, such that if you give a pointer to yourself or a part of yourself, it means that if you ever went away and you dereferenced that pointer, bad things would happen. And so therefore you increment your reference count to indicate that in fact there's a lock, right? You cannot be removed because somebody refers to you somewhere. Okay, so that's essentially how that works. And so in this case, that one reference is due to this dependency. Down here, right, this USB fmask storage, there's two references. In this case, it's probably something file related. You'll notice that whenever you open a file to do with a driver, for instance, that reference count will go up. Why? Because the file operations are cached. Okay, and they're cached such that the rest of your file operations doesn't have to look up what those file operations are. rmmod, of course, is for removing things. You do it by name, not the file name. Again, in fact, you can leave .ko at the end because that's been allowed now, but you're not supposed to. So you'd say rmmod foo. You can actually rmmod more than one thing at a time. You can actually list a bunch of modules to remove. However, it removes them in order. Okay, so it will go through your list left to right. If there's a dependency between bar and blah, if they're in the wrong order, the first one will fail, the second one will succeed. It does not go back. Okay, so the order matters, but otherwise it will remove bar, then blah, then so on. All right, so if you want to do it more than one, make sure it's in the correct order. Depmod is used for figuring out dependencies, and so mod probe, which is what we're about to talk about, requires the ability to know what depends on what. The reason is because mod probe is a smart insmod. It needs to know what needs to be loaded first. And so depmod will figure all these things out, and it will maintain a number of databases under the libmodules directory. Modules alias, built-in, dep, order, and symbols, amongst others. There's also some binary versions of these files that are faster to read. In the case of alias, we maintain aliases for modules. Sometimes we don't care what the name of the modules is, we just really care what it does. And so there's an alias, for instance, for different network protocols. And so we say we want network protocol family number 3, and then it turns around and loads the appropriate module that implements those things. In the case of built-ins, these are the modules that are currently built into the kernel, right? So when you try to load a module that's already a built-in, of course it succeeds because it's already there. Modules dep indicates dependencies between modules. We also have module order. This indicates the actual order that you'd want modules loaded at boot time or what have you. And then you have module symbols. So all symbols, all exported symbols from all modules are listed here so we can figure out those implicit dependencies. All right, and so whenever you run depmod -a, it will go through and completely rewrite these files. If you just run depmod, it will try to do an incremental addition to those files. But we need this primarily because of modprobe. And again, modprobe is there primarily to make our lives easier, but it's also used by the kernel tools in order to load things like drivers. All right, now, and actually it's also used for persisting options. So there's a number of files that are used to specify options passed into modules such that whenever you mod probe a module, it will automatically add those options along the way. And of course, UDEV uses this to load drivers, as I previously mentioned. Now, I'm sure a couple of you have probably done this before and used insmod, but if you use insmod more than once on the same module without removing the module in between, what happens? Does anybody know? You get an error, right? Because you're trying to install the same thing twice, right? So by trying to do the same thing twice, of course, that's bad. So insmod is basically saying, I want to install this module. The second time it says, I can't, you've already been installed. However, if you mod probe the name of a module, not the file name, but the name of the module, and then you mod probe it again, what happens? Success. Okay, the reason why is because mod probe is asking the question, have we satisfied the need of this module? In other words, is this module present? If the module is present, then success. Okay, if the module is not present, we then load it, then success. All right, the only situation where mod probe will fail is if it can't load the module doesn't exist. So the neat thing is that you can just mod probe something madly as many times as you want, and if it's already there, then great. If it's not there, it's put there. But in all cases, mod probing something is completely safe to do because the answer is always yes if those dependencies have been satisfied. And this is true especially for built-ins. You can actually mod probe something that's already a built-in. Why? Because it's already there. Success. However, you cannot insmod them because they're not actually modules. Okay, mod probe configuration. Here's an example of a mod probe configuration. We've got foo.conf here. Here we've blacklisted bar. We don't want the bar module to be loaded. That's bad. It does something we don't like. Maybe it does something that we do at the same time, so there's a conflict. Here we've actually set a set of options for blah, option 1, option 2. And here we've aliased a generic name to foo. So when you mod probe generic name, foo gets loaded instead. Okay, those kinds of things. Mod info is another important thing, and you'll see here that we mod probed the UIO module. In this case, you'll see that it gives you the file name of the actual module itself. It gives you the license, the dependencies. In this case, there are none. It tells you it was built in tree, not out of tree. And then down here we have what's called vermagic or version magic. These were the options that were used to actually build the module. In other words, these are the configuration options used to build the kernel in the first place. All right, so we can see the version of the module, that it was an SMP or symmetric multiprocessing kernel, that preemption was turned on, that module unloading was allowed, and so on and so forth. Okay. Finally, demessage. Demessage is your friend when you're doing modules. Why? Because you want to see whether things work properly, and we tend to use print k to actually see what's going on. The way you see how print k works is you can run demessage, and it will show you all the kernel messages there. Now, the neat thing about the newest version of demessage is if you put a lowercase w after it, it will tail that log for you. So many of you are probably used to typing demessage minus lowercase c and then demessage by itself. You lose history. It's very bad. Demessage minus w, it will just, whenever something new happens, it will pop up. And that's actually a lot better than tailing your log, like a log file, because of course it's buffered. That's basically it. We're going to use, I've basically given you a bunch of indications here on how we're actually finally going to do the labs. Okay, so I've given you all of the answers that you needed in that set of slides to do the 2 labs that I put together. And those 2 labs should take us probably the rest of the time here. If you've already done kernel modules, you'll find them very, very simple. But the 2 labs are essentially building your first module for those of you who haven't done it. So we're basically going to take the module that's already there, build it, load it with insmod, install it, load it with mod probe, right? Play with lsmod. Very simple things. If you've never done kernel code before, those are actually pretty big steps. The second lab is going to be writing 2 modules, one that depends on the other. and then trying to load them in different orders using insmod and modprobe. But again, becoming very familiar with both insmod, modprobe, rnmod, make modules install, and so on. Okay, that's in a separate set of a separate file rather, which I'll bring up in a second. Again, you have access to it already on the website, okay, on the CM website. However, do we have any further questions? Because I know we had a few questions at the back. Yeah, right there. Oh, yes.
So when you go into the menu config and select a new thing like SpyDev, for example,
for instance,
you can put an M and it'll load it as not a built-in but a module.
If you make it a module, yes, okay.
Is that so? When you boot, is SpyDev automatically loaded, or do you have to go in and like start it up?
I see what you're saying. So there's a number of. So I don't have enough information to answer that question. So you can actually load. There's a number of ways you can make that happen. You can list it in the etc modules file, which will essentially allow the boot system to actually load all modules that are listed. In the case of device tree, in fact, by specifying certain things in device tree, it will auto-load certain modules and so on. So there's several different vectors to have those things come in.
Okay.
But unless something triggers that mod probe, they won't be brought in automatically, no.
So if you have a SpyDev reference in your Spy PA handle in the device
believe,
tree, it should automatically load SpyDev.
As far as I believe with device tree that happens, yes.
Okay.
I normally build SpyDev in statically because if you know you need it, there's no point in making it a module.
Right. But then if you do write your own Spy driver, it would not work because SpyDev is currently kind of using the Spy bus, right?
Well, you wouldn't necessarily have both loaded necessarily, no. But if you're writing your own if you're writing your own SPI driver for a particular SPI bus,
yeah.
With device tree being used, essentially you describe what you want in the device tree. It would then auto load your driver appropriately and go from there. And that's fairly typical.
Cool.
Again, in embedded, we quite often build these things in statically if we know they're there.
If you blacklist something in your modprobe file and it's already running, does it remove it, or is the modprobe config only like before you boot?
So blacklist is only used by modprobe at module insertion. So if you're already running a driver and then you blacklist it, you either have to unload the module or reboot for it to be removed. It will not automatically remove it. By changing the file, it has no idea what's already there.
Yeah, I just wasn't sure if you like sourced it again or something.
No.
And what site are the slides available on?
cm.e-aale.org. So in other words, if you look at the hardware kit, it says EALE at the top. The website is just .org at the end. If you add a cm dot at the beginning, or course materials, in other words, CM for course materials, it will work. If you also go to the e-aale.org website, there's a link to everything. Yeah. It is also on GitHub. The link to the GitHub page is also on the web page. Yep. Yeah, our SEO is still new enough that we don't show up in Google very much, but we're working on that. Yeah, when you look for these things, typically it doesn't yet take you there. But okay, so let's pull up the slides. Just for the sake of argument, let's. These are the actual slides. Again, you can get them off the CM site. You'll see that here, in fact, the first lab is, and we're going to do this on the target itself. You can either do this via the Cloud9 interface, or you can do this. Through SSH, the way Jason showed you this morning. Now, there's one thing that you're going to have to install first, and again, you will find this on the website, and that is you need to install kernel headers on your machine. Okay, and in fact, what we're going to do is if we go to cm.eal.org. Now, if you actually have networking already working, the pass-through that Jason was talking about this morning, you can in fact install this using apt-get. You can apt-get install your kernel headers. However, just to make things simpler, we also, apparently everybody's going to the website at the same time. That can happen. Either that or my DNS isn't working properly. Let me just double check that. For some reason, oh, okay. Why? Not entirely sure why, but sometimes that doesn't work. Let's try this again. There it is. Oh, it was a DNS issue. All right, so if you go to cm-eale.org and you click on the 2018, and we go down to the modules Kbuild directory, you'll see in there, amongst other things, oh, I'm sorry, no, we moved it, didn't we? We did move it. There's a common directory. In the common directory, you'll see that there's a, one second here, there it is. You'll see there's a file here called bone Debian 9.3, sorry, Linux headers 4.9.82 Ti R102. These are the ARM headers for this particular board. If you download that file and then scopy it over onto your target and use dpackage-i to install it, you'll have your headers. Now, the easiest thing to do for that, in fact, is to use the USB keys that I actually had intended to pass out beforehand. And I'm just going to grab over here. Instead of downloading things, we can start passing these out. Yes, that is the target. Start beginning. All right, so instead of downloading things, it's probably easier just to get things off here. So again, you can in fact plug this straight into your target. You can have one anyways, it's okay. If you plug this actually straight into your target, you can actually read it straight off the USB key, and you don't even have to copy it over. And so that makes it even easier. There's one for you, and you, and you, and you. It's okay, you can have one. You're welcome. Lots. All right. Yeah. All right. So like I said, I was thinking about this earlier. You can keep these. Yeah. Oh, you have extras. Okay, got it. I'll grab these. Did I give you guys one? Oh, yeah. No, I know. I'm just trying to not lose my spot. All right, so here's one for you, one for you. And here you go, one for you. Oh, do I give you one already? I'm sorry.
When you plug it in, it's not going to automatically mount. How do I mount that?
Has it not mounted?
It's not, well, it might have listed mount.
Okay. Yeah, you might have to type, as root, you might have to type mount. It won't auto mount? Oh, I'm sorry. No auto mounter.
Well, no,
Robert, come on. Ah, fair enough. Does everybody have one? Okay.
Thank you.
Oh, actually, I'll take one. Thinking about it. I'll take one. Okay, so if you actually take the USB key, just to make it easier, if you put it on here, if you plug it in, and I'm actually going to use screen to get onto my target here. So if you plug in the USB key into your actual device itself, I'm going to go make that a bit bigger. It's going to take a second for it to boot. What we're going to do is we're going to install the kernel headers. And apparently it's taking a really long time. There we go. Now, what we're going to do is we're going to log in as Debian. Okay, and of course we're going to log in using temp password or whatever password you change yours to. I've actually changed my password. I'm just going to do this quickly, then we'll get to questions. I've got it loaded, and if we do at ls USB, you'll see that it should be there. You'll see here we have the USB key right here. And what we're going to do is if we actually look in the /dev directory, you'll see that we have a, oh, that's actually the, that is, okay, that's because it's MMC, a block device. Otherwise, yes, that's right. So what we're going to do here is we're going to do a sudo mount /dev SDA1, and I'll just put it in /mount. That's a pretty good place to mount it. So let's just, again, actually what I will do to make it easier for people to see is I'll split my screen. Okay, so if we do this, you'll see that it's going to ask you for your password. Either temp password or whatever you changed it to. As I said earlier, good idea to change it to something you're used to typing, so because you're going to be typing it a lot. And you'll see now if we go under /mnt, we now have the actual directory itself. Now, as I said yesterday, or earlier today rather, there's a script here called update.sh. If we had network access right now, you could actually run that. It would update the file for the latest things on that website. But anyway, otherwise, you'll see that there's actually a common directory. If we go into the common directory, and there you'll see that we have a number of files. One of them, of course, is the header files for this particular board right here, see? So if we now type sudo dpackage -i Linux kernel headers, or Linux headers, right? And press enter, it will in fact install. And in my case, it says it's installing it over what was already installed. I already had it installed. But in your case, it will say unpacking a deselected package or something like that. Okay, so by doing this, essentially you now have a full set of kernel headers on your machine, and it means that you can actually build your own modules. And it also means you're ready for the labs tomorrow when we start playing with I2C labs and SPI drivers. Okay, now sadly, it's not a very fast USB stick, and of course we are on a little tiny embedded system installing lots of files, so it'll take a second. All right? So just for the sake of argument, I guess what I'll do is I will open up another terminal, and I should be able to SSH over onto it just to make it faster. Two, rather. Yes, I know it changed. Apparently I've used a few. Demos are wonderful things. Oops. Okay, so if we go under /mnt again here, it's actually in color now, that's kind of fun. Let's go and actually look at the labs themselves. So the idea essentially with the labs is to start with this default, very, very simple module and go from there. Now, just for the sake of time, since we only have about 20 minutes left, I believe, we could just use the file as typed in the solutions itself. So let's walk through that. I guess first of all we can see whether or not, oh, it's actually finished installing. Okay, so our headers are installed here. So let's go back into the kernel modules Kbuild directory, which is for this class. You'll see, of course, in there that you'll have the labs PDF and in fact the slides that we're currently looking at. We also have a number of different lab C files. These are actually the solutions. If you write it yourself, this is actually, the idea is not to just look straight at the .c files. But the idea here is, just for my demo here, I can show you how it works. If we look at the lab1.c file, all right, you'll see that it effectively is just the file that we talked about before. Okay, it is straight up the init and exit code. Nothing too exciting. if we actually now build it, and you'll see that we have a make file that's there. Okay, you'll see here that it in fact is a native, is a make file for building a native module. In this case, we're not cross-building a module, we're building on the target itself. All right, normally we were actually hoping to show you how to cross-build, but we're going to build on the target just because it's easier. All right, so you'll see here that we're going to build three things. We're going to build the solutions for Lab 1, Lab 2, and in fact, there's 2 files for Lab 2. So right now we're going to concentrate on Lab 1, however. So if I type make, it will in fact do a make modules by default. And so that'll just take a second because it's not an overly fast CPU. But you'll see here it actually compiles, whoops. Oh, that's possible. Oh yeah, you're right. I normally do this in my home directory. Oops. There we go. Let's try that now. You'll see the first thing it tries to do is it tries to build the actual module itself. And you'll see here it's building the .o file. It then actually it's going to build all the .o files. Here you'll see it actually builds .mod.o files. These are actually generated files by the module system. You'll see it generates the .mod file and then it links into the .ko. Builds the mod file, then links into the .ko. So this is actually how the modules are put together. You'll see, I just made it in the home directory. It doesn't matter where you do it. The point was made that we were building on a machine where we didn't have write access to the thing, and that's indeed what the problem was. So by just moving them to your, or copying them to your home directory, in fact, that will solve the problem. So you'll see here we have a number of different files that have been created, mod.c files and mod.o files and so on. However, the important ones are these .ko files. These are the actual kernel modules themselves. And if we now do a ls of star.ko, you'll see, in fact, our 3 C files have actually been compiled into 3 kernel modules. So the first thing that we said in this lab down here is insert the module using intmod. It then says use dmessage to see the print k output, and then it removes the then you're supposed to remove the module using rmmod, and then we're going to install the modules with make modules install, and then we're going to mod probe the module. Okay, so let's wander through that set. Okay, so the first thing I'm going to do is an intmod of lab 1. Okay, and just for the sake of making this a bit more interesting, I am in fact going to run dmessage up here so we can actually see it a bit better. So dmessage -w, and here oops, I think I mistyped my password. There we go. So what I'm going to do here is I'm actually going to do a sudo of intmod lab1.ko. And so what this is going to do is this is going to load the module into into kernel memory. Again, it'll ask me for my password because I'm using sudo. Again, I mistyped it. And you'll see here it says hello module loaded at, and this is in fact the print k that is in our initialization routine. Now, if I do an ls mod, and I'm going to pop that into less just so it doesn't scroll off the screen, you'll see that lab 1 is now the first thing there. You'll see we have our size in bytes. The reference count is 0, meaning I can remove it, and so on. And so you can see that we have all of our different modules loaded on into the kernel memory. Okay, but lab 1 is at the very, very top. Now, if I want to remove it, of course, I could do a sudo rmmod lab1 like that, and you'll see now it says by module unloaded. And you'll see here that when I type lsmod, in fact, the module is now gone. Okay? Now that's kind of interesting, because the interesting thing about it is, of course, we can actually go into that code, right? We can go down here, prinfo, and we can add whatever we want. And it can be print k. Prinfo basically means it's sending an info level kernel log. So we could actually say, hello ELC, and customize it a bit so it's not just straight up the default. And if we type make, now it will rebuild it again, like this, right? We can then insmod it again, right? And you'll see here now it says hello and then hello ELC, right? And then of course we can mod it again and it'll come back out again. All right, we can add arbitrary code in this fashion. Yes?
How sensitive are the Linux headers? I guess what I mean by that is, if you were to go change the kernel a bit and you kept using these same kernel headers, would it not work? Does it have to be the exact kernel headers you use to compile? And how do you make a new Linux headers if you were to change the kernel?
So whenever the kernel is recompiled, you'll find that if the code is actually changed, it will actually change the version.h file. And so whenever you stray from, so first of all, if you are in Git and you are in a clean Git checkout of a particular tagged version, the version will be the tag, essentially. If you start to stray from that, it will be the tag plus a commit. And in fact, if you haven't checked code in and you build a kernel, in fact, at least up until recently, it used to put a -dirty at the end of your version as well. The point is that whenever you make a change to the kernel, the build system knows you've done it. And that's because a new file has changed, and therefore it will update the version string. So if you change the kernel and then try to load a module, again, there's a version magic mechanism that may allow you to load your modules, but more often than not, it won't.
How do you get the Linux headers then recompiled and then moved over to the target?
So in the event of doing a cross-compile situation, if you made a change to the kernel, you would then rebuild the kernel, install the kernel, reboot the system, and then you'd use those headers that you just created rebuilding the kernel to build your modules from that.
Okay, and then, sorry, how are those headers generated? Is that a separate command?
No, as you build the kernel, it configures the headers. The headers are a part of the build. It's just that if you don't want to build the kernel, you can do what's called a modules prepare, make modules prepare, and that won't build the kernel, it will only build the headers. The problem, unfortunately, is there are still certain things that only come along with building them both at the same time. So typically you want to build them both at the same time.
Okay, thanks.
It is certainly possible to build headers and kernel separately, but it's not recommended. Okay, so that's effectively the first lab. And what I think we should probably do is have everyone give this a try. So who hasn't done this yet? Right, so let's try getting this part working first before we go to the next one, because this is probably the most important lab. Right? Actually writing code, getting into the kernel first. You'll find that this actually opens a lot of doors. I'm just going to turn off my... have you done the first one already? Yeah, sure. We can do the second one. Sure. Yeah. So let's go over this one bit again. So again, we can't use the files directly in the file system. I probably went a bit too fast. The whole idea is if you go into your home directory and you make a new directory, right? Let's see, if you just type cd, it'll take you back to your home directory. What you want to do is create a subdirectory into which we're going to copy our code. In this case, I'm going to do a make dir -p source, because that way it succeeds even though I've already created it. The idea then is to copy the source code from where you've mounted it, /mount /modules star to the directory I just created. So by doing that, we're then in a situation where we have a copy of the files that we want to to work with. Now I'm not going to do that because I just made a change to those particular files, but once we go into that directory, you'll see we now have all those files and we can actually build those other bits. Now, the second lab, I would suggest that you write the code instead of actually looking at the solutions. Just move the files out of the way and use the same file names. That way you don't have to change the make file.